And again, after they are done, you just go back and set your, then you know the order. So with that order, so I don't have to come back and forth again. So just go. There's going to be Pro X, you're going to ASME and Milwaukee. So that's.
To go. So our project is the Millport Sigma lifting device. I'm Nate.
I'm Nolan.
I'm Amanda.
I'm Jake.
I'm Harry. So the company background in the current situation, we're working for Millport Sigma, which is a large pharmaceutical company that has a factory here in Milwaukee. They do a lot of packaging of different products and chemicals. And the situation we're looking at is they're taking finished goods off the top conveyor, putting them into a box on a scale, and lowering them into the bottom conveyor there. This is our current situation and how the factory is set up. So the problem that they're facing is that a lot of these packages weigh about 50 pounds, and that's a lot of weight for somebody to be bending over and lowering into a lower conveyor. So they want to automate this process. As you can see, they've already purchased a lift table to lower the box down to the height they need. And now they're looking for something to transfer the box from the scale onto the lower conveyor. Some of the objectives that we have is that our design should raise and lower within 10 seconds. That should be able to lift 60 pounds, including the package and the scale. Should lower to 10 inches and raise to at least 18 inches. And some of the constraints we were given were that the design could not increase the amount of any safety issues, could not tip over packages, and then had to fit within a 3-foot flipper.
So right now our budget by Millport Sigma is $5,000 for our one test stand. And we really, as a team, want to keep this cost low because we will be reproducing this around 40 to 50 times at their other stations. Our current bill of materials is listed in this table to the right. Right now our vendor is listed as Amazon just for our testing purposes, but all of the products are also available at wholesale stores for when we do buy in bulk. Right now our project is coming in under $450, so we are very much so under that $5,000 budget. And then some background information. One of the first kind of ideas that we brainstormed as a team for how to really eject this package off of our lift table was with the use of a linear actuator. So as a team, we investigated 3 different types of linear actuators, including mechanical, pneumatic, and hydraulic. And just for the sake of cost purposes and installation purposes, we went the mechanical route. So 2 types of linear actuators were investigated, including lead screw and ball screw actuators. And while they're very similar in nature, the ball screw actuators have the use of grease ball bearings to actually grease the screw as the actuator is being pushed against the screw. Ball screws also have slightly higher precision rates and also require lower maintenance from the operators on their end. So that's kind of why we are going more in that route. One of the most used transfer tables in industry are actually ball transfer tables. These allow for 360-degree rotation of packages, which is what Millport Sigma needs, especially for the bigger boxes. So they put the stickers on the boxes and have to rotate it, and we're really trying to eliminate that movement, which is what these ball transfer tables do. The one problem with transfer tables like this is that they either come in individual ball bearings, so each of the balls separately will have to be installed, or it comes as one solid table. And as a team, we decided that the individual rollers will be too complex to have to reassemble for each 40 to 50 stations. But the tabletop itself is too heavy for our purposes. Which led us to actually researching the ultra-high molecular weight polyethylene, which is this plastic. It has a very low coefficient of friction, which means that the operators will be able to actually push the packages off of the lift with ease. And then it also has very high strength and it won't dent. It is rated for use in industry for materials such as our chemicals. So we thought that this was a great alternative to transfer table.
So in the design process, after talking to Millipore Sigma on a factory tour, and then also using the constraints given to us by Millipore Sigma, we came up with some preliminary design solutions. So each of us created our own first set of like basic brainstorming designs. So in this first picture, you can see that we chose a ball and screw linear actuator. This linear actuator will push the package off this scale here onto a set of rollerball tables, which would allow the operator to rotate the package, like Amanda said, to put package labels on the box, and then the operator will be able to push the package easily onto the lower conveyor. We ended up choosing this type of linear actuator for our final design, but we did not go further into these rollerball tables. The second design here showing a rollerball table, a pre-manufactured rollerball table adjacent to the scale with another type of linear actuator adjacent on the side of the scale. This has a pulling force, pulling motion back towards the conveyor onto the rollerball table, which then it would catch the box, pull it onto the rollerball table, and then it would hit a pin, allowing the larger box to rotate onto the lower conveyor. This is a good design for the larger boxes that Millipore Sigma has to deal with, because these boxes can only fit on the conveyors in a certain orientation. Otherwise, they're hanging off and they could catch on other lines. However, this is a poor design for the smaller boxes that Millipore Sigma deals with, because it may not catch the correct corner of the box and it will just spin onto the table. This third design here, it is very similar to this first design, just a different type of linear actuator. It'll push the package off the scale onto a rollerball table. That rollerball table has individual roller balls, so we can fit it to the perfect size we need. However, this linear actuator would need to be much bigger to push the package all the way across the table onto the lower conveyor. The fourth design on the end has a prefabricated rollerball table again, but this is mounted on top of the scale, which would allow ease of use when creating the package. The ejection method is an accordion type linear actuator, or like a scissors type, where it would extend across the rollerball table onto the lower conveyor. This design is good in theory, but the scales that Millipore Sigma have currently cannot withstand the weight of the 50-pound package and the rollerball table. And then finally, this fifth design here is more simple. It doesn't have a automatic ejection method, but in theory, the scale, when the table is in its upright position, so the operators can easily package the chemicals, the scale would protrude so that the box can be weighed for shipping. And then as the table goes down, fixed stops will keep this rollerball part up in the upright position. The scale will be below that, and the operators can easily push the box onto the lower conveyor. However, this type of roller is not easy to rotate 360 degrees. It's only one direction linearly. So off of these, we created a trade-off study. After talking to Millipore Sigma again and looking at their factory, we thought that maneuverability of the package is the most important of these designs. So we want to see how easily can the box's orientation change. This is important to Millipore Sigma. They want the best ergonomic situation for their employees. We then looked at the speed. We cannot disrupt the assembly process. So because Millipore Sigma deals with shipping deadlines, we don't want the operators to stand idle while this operation is going on. Then we thought cost was very important because, again, we have 40 to 50 stations. This $5,000 budget, we would like to stay well below that just for the sake of the company. Size constraints. Again, once we did the factory tour, we realized that They do have a little bit more area than a 3-foot footprint, but we still would like to keep that as minimal as possible, just so we don't hinder any of the other stations. Safety, again, is very important. We don't want the work environment to become hazardous for their operators. They have to do this on a daily basis. So we just want to keep them safe. Controllability, this is to be operated by a foot pedal so that the operators can be prepping package labels for the next package that comes up while this one is being unloaded. The ejection device, again, the Millipore Sigma already bought the lift tables, so our scope of work changed from lowering and raising the packages to getting the packages off the scale onto the lower conveyor. And then ease of installation. Again, they have small maintenance capabilities, so this should be easy to and repeatable for 40 to 50 stations. So then we create a decision matrix. You can see that in the first this upper image here. Each member rated each of the designs based on the 8 trade-off categories we selected. We ranked them on a scale from 0 being unsatisfactory to 4 being very good. And then we completed that for every design, like I said. And then each design was then summarized into this bottom decision matrix here, where we used blue as kind of our highest ranking. And then as it shifts from blue to teal to then green and then yellow and then brown and then red, the design became met less of the requirements from the trade-off study. So you can see here that we used Nolan's design. It was very good in most of the categories, except the ejection device was non-existent. So we based most of our final design off of that, and then we added a ejection device to the final.
So here is our final design we came up with, like we said, from the team decision matrix. We stuck with the kind of cavity-like framework around the table, which is represented below by the orange. And the whole point of the framework now is it's going to be made out of 6005 T5 aluminum bracketing. And then we're going to mount this UHMW plastic sheet with a center cavity in the middle for the scale to extrude and submerge below for our actuator to push the package off. And so our linear actuators are along the short ends of the table, and we have a slider bar attached to one end of the actuator and a free sliding mount on the other side to support the weight of the bar. And so in the highest position of the scissor table, our scale will be extruded above the plastic sheet. So the employers can load the package and get it ready for shipment. And then when they use the foot pedal to lower it down, we're gonna, like we said before, we're gonna have some mechanical stop and the bottom, so the table can actually submerge below the set height, and the scale can become flush with the plastic sheet. And the linear actuator will then automatically turn on, and our package will be swept off the table and onto that lower conveyor belt. And to illustrate this, on our next slide, we have a video showing the process again. So just to reiterate, package goes down, foot pedal to lower the table, stoppers will catch the framework at that set height of the lower conveyor belt, and our actuator will turn on and push the package off of the table and onto the conveyor belt for them to be shipped. So like we said before, one of our biggest concerns was either doing rollerball tables or the UHMW for the transfer surface of our package onto the conveyor belt. And so the first way to validate that we're going to use UHMW was to do a friction analysis on the package and between each of the surfaces. So we found that most rollerball tables use stainless steel, and stainless steel is also the surface used for the scale that they have in their packaging line. And then we also use cardboard, and we found a range of static friction values from 0.15 to 0.5. And we were given that with our maximum weight of a box of 50 pounds, this would be our worst case scenario of a friction force put on to the linear actuator. So to validate that our actuator was able to withstand the force of all the friction forces of these packages. We found the force required of our heaviest box for each of the coefficients of friction, and then compare them to our actuator maximum power force output of 294 newtons. And so for our heaviest package and our highest coefficient of static friction, the required force would only be 111 newtons to push, and with our linear actuator being able to supply 294 newtons of force, our selection of actuators should be able to handle each box and package weight.
So one of the other analysis we wanted to do was a tipping analysis on each of the packages. So Millipore Sigma provided us with a few different box sizes. And because we didn't know the orientation at the time, we wanted to account for either length or width being on that actuator arm. And because it's a design constraint, it was important to make sure that none of those packages in any scenario would tip over. So the height of the actuator in our design is 3 inches above the base of the table. And this is where the applied force would be, as seen in this figure. And so we did a basic statics analysis on tipping versus sliding case. And what we actually find is that the height required to tip over a box is actually just a function of the static coefficient of friction and the width of the box along the X here. So as we can see with any box width or length at our applied height, the height to tip is much higher than our applied force. So none of our boxes will tip over during the ejection process. The next thing we wanted to look into was the deflection and stresses. Due to the arm only being driven and secured on one end, there could be a lot of deflection in our arm. It's only freely supported on the opposing end. So we looked at this for 3 different deflection cases. We looked at it as a distributed load, an intermediate point load at the center of the bar, and then an end load for the worst case scenario. Some important assumptions that went into this is that the load acting on the ejection arm from the package would be equivalent to the force of friction required to move that package. We also considered the bar weight to be negligible and the motor end of the bar to be rigid and uniform with the bar and the motor. For the distributed load, we calculated the distributed loads over the length of the box, but actually distributed them over the entire length of the bar to be as conservative as possible. From this analysis, we can see that in each of our different load cases, we have extremely minimal deflection, and that's because right now we use the T-slotted aluminum that's the same in the frame for the arm. Next, we looked into a stress case. So we just calculated bending stresses about those point loads. And if we were to look at the distributed load, it's summed as a point load anyway, so it would be the same as our intermediate center load. And our yield strength for the material is 240 megapascals. So again, with the forces that we're dealing with, we're not really dealing with any significant stresses compared to what our yield is. So for some future work to be done, methods of attaching components to the table. Currently, we have the T-slotted aluminum, and there's some simple attachments that can be made there, but we want to do some more investigating into all the other components. Selecting an injector bar material, as I just said by our analysis, we don't have a lot of stress or deflection, so we might be able to get away with something a little bit skinnier, smaller, lighter for that injector bar. We want to integrate the linear actuator to the existing lift controller. We don't want a lot of buttons for the operators to push, as we previously discussed. We want it to be one process where you load the box, step on the pedal, and it ejects, and you can do something else. So we want to make sure that we can integrate those 2 processes together. The table needs to have stoppers to allow the scale to slip away. We haven't fully decided on how we're going to mount those stoppers, whether it will be directly to the table or on the floor on some sort of guide rails. And then finally, we want to make sure we test that poly for the true coefficients, because right now what we have is just based off of research and estimates. We'd like to get some experimental data work on what it actually would be.
Yes.
Yeah, I can start a couple of. Okay, yeah. First of all, on your budget, you talked about like it's 400 and something, right? That does not include any labor, right? For
Yes.
installing and all of that, right? So,
Yeah, those are purely just parts.
Millipore Sigma also has a maintenance team that they plan to assemble using them, so
do you have an estimate of what that's gonna cost?
No.
Because your time is free, I know, but they have to pay.
no, we don't have an estimate on how much that's gonna cost, which is why we want to keep the assembly process as minimal as possible, because we know their time is valuable.
And how confident are you on your coefficient of friction, static friction that you use or dynamic friction that you use?
The range of frictions.
The range of friction. First of all, wide range of frictions. Of course, always there is a range, but
Right.
how
So
confident are you on the calculations that you made in that regard? And I have another question that's gonna come right after.
we're fairly confident in this range because again, we did this based on experimental data that's out there. So like, for example, I think cardboard on steel was 0.5, and then most of the UHMW, there's not like specific material on material friction coefficients out there that we could find, but generally they were ranging from around like 0.14 to 0.2. So that's why we wanted to go over the broad range. So I mean, we could potentially extend it even further, but based upon what we could find, we thought that this range would cover generally every case.
Yeah,
But you know, you have access to both of your materials, right? You know exactly what cardboard is, you know what material you're gonna be. Why not experiment and figure out what that's going to be?
That's what we're going to be doing in our future testing phase. We actually couldn't purchase anything until Millipore Sigma figured out how the purchasing was going to work. But we do plan to buy those sheets of plastic starting this next semester, actually, and running that experiment.
I think it'd be a great, you could have just picked some pieces to do it, but I think that will be probably one of the preliminary calculations that you're gonna do. Then, you're talking about bending, deflection, and you're talking about deflect. Could you show me a free body diagram of how those forces are coming, and beside that element that you have, how those forces are coming and where you're calculating those forces, and what are you worried about bending, deflection, why not buckling and all of that stuff? So just maybe take a couple of
Right.
minutes.
Okay. So as far as what we did for this, again, we were assuming that the boxes would be centered above the bar for this analysis. So for the distributed load case, we calculate what the force of would be along this length of the package, but we distribute the load over the entire bar. So that's for the distributed case. And then based upon how we solve with distributed loads, you can assume them as a point load centered above the bar. So we converted it over its length to a point load at the center of the bar. And then to find the bending stress, we calculate the moment from the end of the bar to where that point of application is. And then using MC over I, we calculate the bending stress.
Maybe I got it wrong, but are you talking about you get the box, put it on the platform, and then you're finding deflection underneath, or are you finding the deflection of the?
So the deflection on the push arm here, we wanted to make sure that as it's pushing on the box, it doesn't bend too far backwards.
Yeah, I see. So that's the way you're pushing.
Right.
I thought you talked a lot about point load, so it's just that.
Right.
That's.
Right, so yeah, I should have clarified. So right here is where like we would assume the box to be, and we
I
assumed
see.
it as a point load or a distributed
I
load.
see it now, yeah. And the ends are pretty much.
So this end is fixed, and that's what I was saying with that assumption. So when we do that stress calculation and bending calculation, we assume that this bar is fixed with this end, and like this is a rigid piece.
Okay.
And then this end is a free end. This is just gonna be another UHMW block on a guide rail. So it's a free sliding end.
So it's very basically a cantilever beam.
Right, exactly.
How much clearance is between this picture and the conveyor that you're moving to?
So right now, the conveyor is about 9.5 inches off the ground. And then we have a rough 3x3 footprint between the computer station and the package labels and the conveyors. So we have we plan on putting this as close as possible to the conveyor, but we also have a plan on having this bar kind of extrude past the linear actuator stoppers so that it can breach that gap and push fully onto the conveyor without the box overhanging, like we mentioned before. So there's probably gonna be a 2-inch gap, 3-inch gap between the conveyor and the tables.
And is that, okay for the small packages? What's the smallest package?
The smallest package is like a football size. So right now, the operators are taking it and just kind of throwing them underneath the on the smaller conveyor. But this should work for the smallest package as well. Hopefully it works.
Could you imagine it tipping and kind of getting stuck there,
Yeah.
depending on the geometry, right?
And also the smallest packages, they're nowhere near the weight of 50 pounds, like the heaviest or the largest packages. So maybe if the operators do want to save time, it'd be quicker to put them under there themselves. But we see where they want to save their backs and stuff with this.
Are there any questions from you guys?
Why did you choose 6805 T5 aluminum full frame slider?
So we kind of it made our analysis a little bit simpler because there was actually a website we found that gave us for our deflection analysis stuff, it gave us the mass moment of inertia for the properties of that set aluminum with the dimensions and everything. So it made it that simpler like that too. But we were going to do initially the 8060 aluminum, which is on McMaster with the T-side bracket. So that has like all those already threaded mounts and stuff in them. So it was easy installation for it because we want to make it as repeatable as possible. But this uses the same set of mounting stuff and it gave us all the numbers and stuff for our analysis already.
Next question.
Yeah, so I think mine is sort of similar to Dr. Williams. So you talked about the scale dropping down below the surface. I guess I'm sort of concerned like with a small package, if it's dropping below, wouldn't it get caught on like the difference in height?
It's going to be flush to the surface.
So it's gonna be perfectly flush.
As close as within tolerance. Yeah.
Okay.
The scissor lift table that they use is actually the height of the platform itself is 6 inches off of the table, and it can go all the way to being 6 inches of height. And so with the 10-inch conveyor, we have that 4 inches of leeway between. So we're going to put in those, like we were saying, mechanical stoppers on that framework so it can be flush so those small packages won't fall through.
Any other questions?
Just one more. For like the ball screw versus lead screw, would you consider doing a lead screw in the future? Or did you see a big price difference between like those? Because the ball screws seem like pretty fancy. I don't know if you need that much precision, but was there a big cost difference for them or?
Kind of the amount of power that we need, there wasn't necessarily that big of a difference.
Okay.
So the two that we were really looking at between the lead screw and the ball screw had maybe like a $50 to $75 difference depending on the vendor. But with the budget that we have and with the amount of uses that it'll actually need, we just decided to go with the ball screw for quality aspect.
Okay, that's not.
Did you check the coefficient of friction between the box and the conveyor belt you're pushing onto? Because for that last half of motion, you're gonna be pushing across much higher coefficient of friction.
Also it's instead of like a conveyor belt, it's like if you go back to the preliminary.
They're like roller pins.
They're
automated pins.
They're roller pins that are some of them are powered and some of them aren't. So these are like the conveyor belt and I'll just push on them.
Friction.
Yeah, it's not.
It's not friction.
Yeah, I got a question. So if you're pushing on the rollers like that, but some of them are moving, you have to make sure that the box is on there fast enough so that it doesn't grab it.
Yeah,
Right.
That's also one of the constraints is to get it on there as fast as possible. So the whole motion completes within 10 seconds, I believe. So we do have enough force and the linear actuator we did decide on it is capable of getting it on there fast.
Yeah, that was one of the primary concerns with these first designs is we wanted to make sure whichever actuator we used, the speed was fast enough. So we were kind of concerned that like a general like electric piston might not be fast enough, which is why we went with the slider on.
Next group, please come and set up. I have one more question from you. Just what you talked about 360-degree. I didn't see anything on your design, but wasn't that 360-degree?
No.
You're talking about 360-degree rotation and all of that thing, and your design is just pushing it to raise the cross.
We're gonna be redesigning the station a little bit to bring the table forward so that they can orient the box, so they'll no longer have to spend. A little bit.
But it wasn't proposed yet at that design.
No, that design is going to be, we won't rotate, we're just gonna redesign how the station's laid out, so that'll no longer be an issue, because they just need to rotate the box to be able to package it.
The whole,
It's gonna be available to them.
the whole station is movable. Like they essentially gave us the ability that they said, you guys can move this around however you want. So we can set the table how we want.
Thank you, guys.
Even step on the other side. We all within.
Generally, no, generally the two closest to the screen will be on, you're kind of on, you're not,
Flip around that.
yeah, yeah. Like right now, there are all four of you on there, but
Nice, that's what's that. That works.
Whenever you're ready, you can go ahead.
All right, hello, everyone. Thank you guys so much for coming to our presentation. Today we'll be talking about our senior design project, the industrial vegetable peeler / processor unit in collaboration with ProX Foods. So we are all senior ME students here in Missouri. I'm Riley Jans.
I'm Colin Seachley. I'm Carmen Leary. I'm Peter Schaubel.
So just go into a brief overview of what we plan on talking about today. First, we'll get into the background of the industry. Why did it go back? The design specifications, the concepting that we went through, our finalized design, some analysis that we have done on that design, and also our next steps going into next semester.
So starting out with some of our background, potatoes are obviously one of the most popular root crop vegetables that exist. And it makes up about 30% of all the vegetables that are produced in the US. And this being the case, it is a $4 billion industry, and there is quite an industry for it. Peeled potatoes specifically have many applications such as chips and fries. We got a graph right there representing the average percentages of each application. And it's not surprising with on average, Americans eat over 112 pounds of potatoes in a year. That brings us to our problem statement that we developed after analyzing our requirements, which was to make an automatic root vegetable and potato peeling device with a 1 ton per hour yield, which must be safe to maintain and operate. The device needs to be able to move the vegetables throughout the machine and remove the outer skin of the potatoes and polish the underlying flesh. Waste produced must be peeled, waste produced must be removed from the system and managed accordingly, and it also must be food safe. Later on in the design process, we were also given the requirement by our ProX that the device must combine the functionality of both a peeler and polishing machine and must meet or exceed performance of existing machines that are in the industry. Some of the types of machines that are in the industry that are used for peeling are steam peeling and abrasive to knife peeling. Now, steam peeling is a relatively quick application. But it's used in higher load applications such as 5 tons per hour, which was higher than what our requirement was. But it has a high cost for when compared to other applications in the industry. But it also has a high material removal rate. Now, knife peelers and abrasive peelers, these both use an auger to move vegetables throughout them. It's relatively a lower cost for the application, but it also has a lot lower to yield. These typically result in about 80% removal rate. The way abrasive peelers work is that the potatoes are rolled over spinning rollers that are coated in abrasive, while the knife peeler has a drum that has blades that are spinning to remove material as well. Should also be noted that ProX currently does have their own abrasive roller and knife peeling unit, but currently that application requires some method to transfer the produce from one machine to the other.
All right, so now we'll get into some of our design specifications. There are 2 main design specifications that we were asked to meet from our client. The first being that it must have a hand peeled finish as it exits the machine. So that left image there is kind of the finish that they're looking for. That is, many customers will actually pay for a higher price for that because it looks more desirable. And our other specification that we were asked to meet is that we must have a 1 ton per hour yield rate. And that is talking about the flow of material that the flow of vegetables that is coming out of the machine. So you input like X amount of potatoes, but the outflow must have a 1 ton per hour yield. So that's not accounting for the waste that is lost. So we started our analysis by looking into what makes a potato peeler a peeler. So we identified 3 key elements of these machines. First being the peeling/polishing mechanism. The second being the waste management, and the third being the device that moves the potatoes or the vegetables throughout the machine. So it's important to control the rates of the potatoes as they move throughout the machine so that you can get the desired amount of finish. It's entirely dependent on the time it takes to get through the machine. So this is a very important element. So we'll get right into concepting. So we spent a lot of time in the beginning of the semester concepting. We each came up with 15, or not each, but we came up with around 15 designs in total, which we then showcased to the client for feedback. So this preliminary phase of the concepting was spent mostly just coming up with new ideas on how to approach the problem, either be that through analyzing individual systems in the entire machine, or by just repackaging existing geometry into like a final package that combines both peel and processing. So we showed these ideas to our customer and we got some feedback. One of these ideas in particular that we showed was a completely new method to peel potatoes that is not used in industry through use of high velocity water streams with abrasive particles, kind of like almost sandblasting a potato to peel it, as if you will. So our client actually found this idea intriguing and they wanted us to do some research on this. So that brings us to our next slide here, where we did a little impromptu qualitative experiment. So basically we fixtured a potato to a board outside and we hit it with pressure washer. We tested various different spray patterns to analyze the different effects. What we found was that under all cases, the high pressure water was able to removed the skin after some amount of time. The time it took was dependent on the flow setting of the jet. And but as we had kind of anticipated, the outerlying skin of the potato is of higher density than the material underneath. So once the skin was breached by this water, the potato was almost immediately gouged and destroyed. So this is actually highly undesirable, as you can imagine. So after this, we did not consider this a viable solution going forward, but it was still a good test. So after that, so after our first meeting with our client, we took those ideas that they liked, and we started to incorporate them into one machine. So for example, perhaps we gave them an idea of how we could do a peeling unit and how we could do a processing unit. We then took the ones that they liked, we combined them into one machine and used that as kind of the basis to go forward. So this stage of the design took much longer than the rest. We spent multiple weeks on this as we were going back and forth with feedback from our client. But in the end, we got to a place that I think we're both very satisfied with. So anyways, now we'll get right into the design. So the first thing we did with our was get into the decision matrix. So I'll explain how we did it. First, what we did was we took, we have all of the different assemblies here, so like the peeler, the polisher, the waste management, the conveying, and the geometry of the device. We tried to come up with at least 2 to 3 concepts that we found were the most viable for those, and we wanted to analyze them against one another. So we came up with a list of criteria that our finalized design must meet, and we assigned a weighting to each of those as to how much we perceive that criteria to be important to the overall design. So the weighting ranges from 1 to 4, where 1 is it's needed, but it's not as important, to 4 being critically important. Each of the ideas were then given us a score as to how we feel like it satisfied that design. So the scoring ranges from 0 being fails to meet this requirement to 3 being it exceeds the requirements. So with that, it was given a score for each of these categories, and then it was multiplied by the weighting and then summed to get a finalized answer, which is in the total section on the side here. So basically, this allows us to give one singular number to an overall design that we can then use to compare it to the rest. Typically, the idea that had the highest score was the one that is perceived as being the best design, but that doesn't necessarily mean that we ruled out the rest of the designs, because we did end up revisiting many of them later on as we were working our way through design. Anyways, I'll turn it over to James.
Yeah. Following the results of the decision matrix, we decided to compile our proposed design ideas into a CAD model. And after a few rough iterations, we ended up here. This is, of course, conceptual in nature, and following some of our later experiments, we will be able to scale this up or down as needed to meet the minimum yield of 1 ton per hour. So you can see what we have is a combination of 2 peeling mechanisms. We have a U-bed roller style abrasive peeler and a rotating drum style knife peeler polisher. Each of them is driven by their own independent auger. That allows us to retain the advantage of having separate machines where the feed rate through each can be tuned to get the ideal result, but it allows you to remove or combine a number of features, such as the conveying of material between the 2 machines is now taken care of internally instead of requiring additional equipment. Also, the functions of waste management are combined underneath the machine into one unified system to be pumped for waste collection. Water spray is also now, which is not modeled here, only requiring one unified pump system. You don't need to have a separate one for each machine, and now that helps reduce costs. We also considered how we might improve maintenance beyond what exists on current market offerings. So due to one end of the abrasive rollers being inaccessible, because really it's tucked inside between the machines there, you would have to go underneath any of the existing designs to remove those abrasive rollers. And we consider that to be really unergonomic and a violation of safety, which is very important to this project. So we developed a system where we would have swinging arms, which are able to be in either an operation position for running the machine or a service position where they could be easily removed. Essentially, they can be pinned in either position, and an overcentering gas spring opposes the weight of the arm and the rollers to hold them into either position. So that once an optional lever is installed, an operator can easily swing these arms out and then have them readily accessible for maintenance. Additionally, we have the arms pivoting on a stationary or dead axle with an idler pulley, and this allows our motor power to be uninterrupted when you swing these out. Not that you want to power it in the operation or in the service position, but this means that you don't have to disassemble the bearings, belts, etc. when you switch between positions if you only need to service the abrasive rollers. So we consider how these rollers might come out without removing the bearings, because typically these abrasive rollers are going to need much more regular maintenance than a well-spec'd bearing. So essentially, if we look in the first image on the side opposite from the pulleys, a supporting shaft can be slid partially out, as seen in image 2. Then this allows the auger or the abrasive roller in image 3 to be slid off of the shaft on the other side, so that, as seen in image 4, the abrasive roller is suspended now between the two shafts and can be simply removed, and the bearings are left intact, only to be serviced if necessary. Following the knife polisher construction, this is a reverse engineered idea from 2 different companies, one of them being ProX. So on the left, we can see one construction style where each side of the polygon-shaped knife peeler drum is constructed from its own separate plate, which houses the knife blades. ProX's design has multiple of those sides combined into one part. However, their panels are not removable. They only swing out for maintenance. We decided to take the best of both worlds and allow the panels to be comprised of both multiple sides and also removable, so that knives can be serviced or replaced off the machine in whatever situation is the most ergonomic and effective for the technician. So we wanted to consider the motion of the product through the machine, and part of that was making sure that there were no dead zones and that our product was under continuous control of the machine or otherwise, accounted for. What we wanted to avoid was the possibility of an already abrasively peeled potato bouncing back into the abrasive peeler after it's already left, or getting any undesirable bulk motion. So immediately our thought was we wanted to butt augers up end for end, and that this would give us full continuous control. So we analyzed both 2 traditional augers and 1 left-handed and right-handed auger butted up against each other. In both scenarios, there were concerns with pinching, crushing, or damaging the product at the handoff between the 2 augers due to the interaction of the ends of them. Additionally, at certain intervals, there would be a dead zone right on that immediate area where you could bounce back from one process to the next. So resulting in this resulted in us deciding that we needed to put some sort of a gap and a secondary transfer mechanism between the 2 processes. This is a cross section of the machine and the path of the product as it goes through. The way that we solved this issue was increase the diameter of the drum peeler slightly relative to that of the abrasive peeler. This allows us to ensure that no potatoes or any other products will bounce back from the drum peeler into the abrasive peeler, and we have control over the order and directionality of the process. Regarding the waste, these will be funneled all into a unified hopper underneath the machine and then pumped to a screw press, which is a machine that ProX and other companies do make. Essentially, what a screw press does is it dewaters our waste, which in the case of potatoes will be peels and starch water, and allows that water to be recycled back into the machine to lower your utility costs as opposed to spraying constantly fresh water. We'll go into later why the water spray is important for this process. The abrasive and knives don't work well without it. Further development will be needed here going into the future, such as developing this hopper further and speccing out what sort of pump is suitable for filtering peels and pumping starch water.
All right. So after we came up with the general concept for the design, we decided that we would need to perform engineering analysis to make sure that it was within the order of magnitude that we knew that it should be. We had a general idea for the footprint. We had a general idea for how big and long it needed to be, and for how long it would and kind of for how fast the auger would need to go. And so the first parameter that we decided to focus on was looking at the RPM of the auger, because we have these two rotating augers within this machine, and we know that we need to meet a certain yield output. And so to do that, we needed to look at what density of potatoes is needed within this machine to get the auger RPM down to a reasonable rate. Because if you have these augers that are very heavy, spinning in there at 60 RPM, 100 RPM, that's not a properly spec'd out machine. And so we took a control volume analysis look at it. We drew a control volume around the entire machine. We looked at the mass inflows and outflows. We have the mass of the potatoes in, the waste out, and then also the yield potatoes. And the mass of the potatoes, or the mass of the potato waste, is just the product of the two yield percentages of the abrasive and the knife peeler multiplied by the inflow. And so to perform the analysis, I introduced a new parameter, which is the number of potatoes per pitch of the auger. And the way that we determined the length of the pitch of the auger was, as a group, we decided that the diameter of the auger is 1 meter. And looking at typical auger offerings for this sort of purpose, a ratio of 3/4 for pitch to diameter is typical. So for every 3/4 of a meter of the auger, we wanted to look at how many potatoes there would need to be to get a reasonable auger RPM. And to do so, we coded this in MATLAB, and we generated the plot that can be seen on the right of the screen, where you can see that for roughly 60 to 65 potatoes per every 3/4 meter pitch of the auger, you need to be spinning the auger at roughly 2.5 RPM to meet the mass outflow of the machine. And we determined that this was a reasonable parameter that could be tuned if needed. The second level of analysis that we performed was on the gas springs, because we have these roller arms that are attached to the abrasive rollers that are then attached to another set of roller arms at the back. That all comes out to a lot of weight, which we rough estimated as around 200 kilograms. And given that an operator is going to need to be opening and closing this, we knew that we would need to introduce another mechanism to assist them, which is where the gas spring came in. However, we knew that we would need to size the gas spring to balance out the load of this heavy apparatus. And so the first level of analysis that we performed on the roller arm was speccing out the size of the gas spring. And to do so, we took our roller arm, we created an idealized FBD, and for this analysis, there was no F operator. And we took the moment around A and calculated the gas spring force that would be required at every angle from the open position to the closed position. And from there, we found the required spring force. And then we took the moment at A again and looked at the force that would be required from the operator to close and open this machine to make sure that we weren't asking them to generate like 300 pounds, that we weren't asking them to do this tremendous deadlift every time that they needed to close this machine, which would be unergonomic and possibly damaging. And we found that the max force required from the operator for our given parameters was around 10 pounds or 50 newtons in that plot, which we found to be perfectly reasonable. And some of the further analysis that we plan on doing in sizing this machine is on the length of the peeler. Because we know that it needs to be a certain diameter, but we also know that it needs to be a certain length, and that's going to be a function of the time that it takes to peel, where that function is as of currently unknown. And to better understand this function, we performed a preliminary experiment on abrasively peeling the potatoes, where we took some sandpaper and potato and just peeled them by hand. We learned a couple things from this experiment, such as the effect that the grit of the sandpaper has on the time that it takes to peel and the ease of peeling, and on the effect that the water spray has on this entire process. As if you peel these potatoes continuously without water spray, it gunks up the abrasive almost immediately and you no longer can peel effectively. And over the course of the second semester, we have a couple planned out steps, including creating fully detailed CAD of each subsystem, which can be manufactured by an external fab shop, the assembly of all the subsystems, a planned analysis on the machine to make sure that the lifespan of the machine and each wear component is sufficiently long, in prototyping each, the scale models of the abrasive and knife peeler and prototyping the auger transition to better understand how that works. Questions?
You may have addressed this at the end when I was
Yeah.
focusing on my notes.
Yeah.
How do you have two internal machine operations? How do you plan to synchronize? Did you say that? Like the flow rate, because they're not the same, right?
So the way that it works is you have an external flow of potatoes going into the abrasive roller. And you want them in there long enough to where it's going to fully peel. And so you're going to tune the abrasive peeler auger to do that. And then once it reaches the slide, I'll go to the cutaway point. Yeah, this one. So this is a good graphic to explain it. So they come in here and you have this auger tuned to get the proper peeling. And then once they hit this drop point, they go through here and then they go into this machine. And this machine is also tuned so that you get the proper time in this machine. And the other, I think what you're kind of asking about is the speed that the rollers and the drum are spinning at to make sure that there's no kind of undesirable interactions, which is largely something that we have to analyze next.
So just so they're
Yeah.
both
Yeah.
working with the same mass flow rate, right?
Yeah, part of it is the knife peeling process is a faster process than the abrasive process, which is part of why it's shorter in this model. So essentially, as long as the knife peeler is moving potatoes through more quickly than the abrasive peeler, it won't be an issue.
For the water cutting, I was just curious if you researched the, like they have water cutters. And the way they work is they're tuned with the frequency that matches the potato feeds.
Really?
Right? And they cut right through stuff, right? So I was curious about that and whether you looked at tangential water jets on the potato.
Yeah, we considered that briefly, but it was a matter of the quantity of potatoes required, the complexity of the machine that would be required to handle them individually, which a lot of our concepts addressed, individual handling of potatoes. We decided that was beyond the scope of what was reasonable within this project.
We're also trying to keep a solid or a nice finished product, so we're not trying to exactly just cut half. As we said before, once the skin was broken, the pressure of the water gouged into potatoes.
Yeah.
So are they gonna build it on like source that to someone else you said, or are you guys gonna build some stuff?
Yeah, I can cover that. So that was kind of one of our first questions that we asked them. Prox as a company actually doesn't build a lot of these machines in-house. They send a lot of it out to external fab shops, and that would be what happens at the time.
Yeah.
So
Cool.
But whether or not they choose to build it is dependent on whether they like the design and see value in what we've produced. We ourselves will be building some scale prototypes that we can kind of do some analysis on it ourselves. But it's up to them to go forward with the project.
Yeah, cool.
The existence of baby potatoes is very nice for scaled prototypes.
You have to consider like the amount of good potato going into the waste.
yeah, so that has to do with the yield percentages. And that's actually one of the reasons why steam peeling, which we didn't really cover here because it's not used for this application, is so important. Because with steam peeling, it results in almost 100% of the good potato coming out. With this abrasive and the knife peeling, in the abrasive peeler, the way that it works is basically the potatoes basically just roll against the rollers. And
Tumbling.
yeah, they're tumbling and then they're also kind of scraping against each other. And that process just kind of scrapes all this potato off. But it's not like you're only scraping the parts that haven't already been scraped. You're scraping a lot of the parts that already have. And so you're getting that yield percentage where you're not getting all of the good potato out.
And it's also a huge function of the quality of the potatoes going in, how much needs to be removed. And so that's why the tunability of each component individually is so important in this process.
After you guys have pressed out all the water, what do you do with the replace? That's
Waste would just be disposed of as any other industrial waste, but it wouldn't be watered, so you don't need to worry about, the utilities or anything, putting that in that system.
Are you planning on having all the skin removed in the first section?
Most of it. You can,
That's ideal.
yeah, largely the abrasive section is for bulk skin removal, and then you do want to hit all of it again in the knife peeler, but the knife peeler is mostly for that finish. Yeah, so.
Yeah, if you only use the knife peeler, your yield percentages would be really bad. Like nobody would buy this machine from you just to peel it for with the knife peeler, because your yield percentages through the abrasive peeler are better than the knife peeler, but you need the knife peeler to give it that surface finish.
So looks like it's cane cut.
Quick question. How would a maintenance operator access those like polling pins for the rollers?
The pulling pins for the rollers?
Yep.
Can you go back to the slide where it swings out? Back. There we go. So essentially, you can see,
Sorry, I think I meant wrong, like the, sorry. Sorry, talking about, you need like the polling pins, like the actual like rollers when you take them out, like when you take a roller out or when you take to replace it, so.
you're saying how would they access these pins?
Yep.
Okay, essentially the way that this is modeled is there's a snap ring clip on there that allows them to shift out, but once this abrasive roller is removed, those shafts can drop out, you can replace them, service them, anything you need, and then the bearings are freely exposed for service as well. So it's just a matter of, it's all accessible, you just don't need to do any more disassembly than necessary.
And if you go back to the other slide too, we have the, so originally all the rollers are kind of in this U configuration, but that's very difficult to maintenance. So we basically have them, those pivot arms, so that they're about at waist height for the operator to access without needing to, climb under the machine.
Kind of like a reverse door.
It is, yeah, it is a 2-operator process, but it's still much more easy to maintain that way.
Next team, please go ahead and set up yourselves at 9:30. Any other question, just quickly they can answer?
Well, thank you, everybody.
I think these guys are taking a little bit longer time. You guys talked about a steam peeler and you didn't use it. So you'll say, why didn't you ask this question for the whole semester from me? Okay. Or from us? Basically, why not reduce the size of the peeler? Why not just, all you're saying is 5,000 pounds, 5,000?
So
Wow,
you
5
need
pounds.
pressurized steam. So you basically cook these potatoes in a pressure vessel where you then run hot water over them and then you need to depressurize it. And the cost involved to build this pressure vessel and then also build the steam system and the depressurization system only makes sense if you're handling more than 5 tons.
Mostly on the steam box.
Yep, so it's just the financial calculations.
Additionally, our customers would much prefer a continuous machine where basically the flow of the potatoes throughout the machine is just always happening. With a steam peeler, that would be more of a batch peeler style where you inload a certain amount of potatoes, you wait for it to do its thing, and then you unload them. So that our customer would also just prefer that level of configuration where it's continuous.
All right, thank you. Are you guys ready? I owe you a couple of minutes. Go ahead.
I'm Ledger Bergeron, Kevin Ludwig, Thomas Schultz. I'm Jonathan Warren.
I'm Aaron Nichols.
And I'm Joseph Kapp. We are the ASME Senior Design Team. We are competing in the ASME Student Design Competition. This year's competition is to create a robot playing around a mini golf. So the field is this, as you can see here. It consists of 9 holes and 7 starting tees. Your robot will start on those tees. The field consists of 6 obstacles that you can putt the ball through just by along the ground. And then 3 of the obstacles the ball has to be chipped through. That's this obstacle here, here, and here. And this is outside the playing field. The game consists of 2 rounds, an initial testing round designed to eliminate all the teams except for the top 16. And then those teams go into a bracket style elimination round. Your scoring is based off of the number of holes completed. If everyone ties on that, it goes down to the number of strokes to complete those holes. And then if there is a tie in that, it goes down to a robot sizing factor. During the initial elimination round, you can get a bonus on your score by completing 2 pre-competition videos. That goes into the pre-competition factor. The first video is a design concept presentation that will be submitted 4 weeks before the competition. And the second video is a demonstration on a full field that is submitted 2 weeks before competition. Here is the bracket style elimination round. That's the brackets. The better your score in the initial testing round, the better your seed is in the bracket. General rules for both games. There's a maximum of 10 minutes to complete a round. The robot must be able to completely traverse the field by itself. The biggest obstacles to that are this board here that's about 4 inches above the field surface, has to go over. It has to go over this 2x4 here. And this part at the end is a sand pit. The robot must not traverse while be traversing the field while it's in control of the ball. So it has to have a separate aiming and shooting mechanism. It must fit within a 50 centimeter cube, but again, that sizing factor adds bonus points for anything under that. Penalties can be gotten if your robot gets stuck. That is a 1-stroke penalty plus a 30-second time penalty. And if you shoot the ball outside the field at any point, it's a 4-stroke penalty unless you're shooting for this hole. And that's our initial constraints going into our research.
So for our initial background research, we started out with the idea that we were going to hit the ball like you would normally in golf, like with an impact. So we looked at different golf head designs. Like Joe mentioned, we have to chip the ball somewhat. So we were looking at like angling the face backwards so we get that normal force going upwards. Also, if we use like a convex face, we can get spin on the ball, or even using a flat face, you can also if you hit off center. And then that spin will create a Magnus effect, which will create a force perpendicular to the travel of the ball. Let's do the next slide. Yeah, so when we put spin on the ball, we put on like backspin, we can get a force of lift. The faster we hit the ball, it'll move the separation point up on the ball, which will increase that force of lift up until we reach turbulence. And that occurs at a critical Reynolds number of around like 21 meters per second. Then up there, you can see the different trajectories that the ball takes for different spins based on the how convex the face of the club is. And then we also designed an initial testing stand where we were going to test the different head shapes and materials and shaft lengths and stuff. Because a lot of the balls are proprietary, so they won't tell you what material they're made out of or different properties about them. So it would give us like the coefficient of restitution and other properties. So then like halfway through the competition, there is a rule clarification. So we thought you had to impact the ball to impart the energy very quickly. However, they clarified that we could intake the ball and shoot it and manipulate it within the robot as long as we're not driving. So we began researching other shooter mechanisms like a double flywheel shooter or like a catapult. So the advantages of like our double flywheel shooters, we could put a specific spin on the ball. Depending on how we orient the wheels, we could do like a top spin or a side spin. With the single flywheel shooter, it's a lot simpler. However, you can only put on backspin and it's going to be relative to the velocity of the ball. And then we also looked at like a catapult or a spring shooter where we'd use like torsion or compression of a spring to launch the ball. And then from there, we moved on to our design objectives.
So our primary design objectives were pretty clearly laid out by the rulebook that we were given by the ASME SBC committee. Obviously, the overall goal is to launch the golf ball through all 9 obstacles. However, in order to do this, we have to build the robot that can navigate through the playing field. And this includes going around the obstacles and in between the obstacles and the walls, And then we also need to be able to climb over the 4-inch elevated platform seen here and the roughly 3.5-inch 2x4 that spans this length here. Also needs to be able to successfully move around a surface, which we probably won't know until the day of the competition. So that could be hard tile floor or it could be carpet. But we do know that there's going to be that sand pit at the end, so you have to account for that. The robot also has to fit within the sizing box, which is 50 centimeter in length, width, and height. And it has to be controlled remotely by an operator, so it doesn't have to work autonomously. We can have a single operator standing outside, and the controller can either operate wirelessly or via a tether. And the different scoring systems with the 2 different types of rounds results in some slightly different factors that you have to consider, with the initial testing round favoring speed and the elimination round favoring reliability, since you don't want to miss shots. So from this, we determined our target specifications. The size is limited primarily by the bounding box. However, we found, based off of the dimensions of the course and the obstacles, that we needed to have a robot that is no more than 36 centimeters in width in order to fit. We also have that 4-inch wall that we have to climb over, so we have to design the propulsion system to accommodate that. The ball manipulating mechanism has to be capable of a horizontal cut, where the ball stays close to the ground, but it also has to be able to chip the ball at least 15 inches high, which is based off of obstacle H, which is basically this tube, and we have to get the ball through the top so that it rolls out. And then we also have obstacle I, which was that ring outside of the field, which is 4 feet outside. We determined that the position tolerance would have to be within 2 inches side to side, because all of the tunnels that we have to fit through are 6 inches in diameter. So as long as we can get the ball within that plus minus 2-inch range, then we're guaranteed to go through the tunnel. And our longest shot would be 6 feet. So we said plus minus 2 inches over a 6-foot shot. And then we decided that as long as we can get the distance within plus minus 6 inches, then we'd also be guaranteed to get through the tunnels. This is less important since we just have to go through. We don't have to determine exactly where it stops. And we initially had an additional specification, which required high maneuverability. This was because when we were designing a golf club type mechanism, we had to be able to line up the robot in order to get the angles correct and to get everything behind the ball. But since we changed our design to something that can pick and then aim and then shoot, we decided that this maneuverability specification was not important.
So in order to meet those target objectives and constraints, this design process that's summarized here was followed. After doing research, each member came up with their own individual design that was presented in front of the team. The team then created a list of pros and cons that was compared directly to the objectives and constraints list. If there was any conflictions that were generated, a concern was made. If there was concerns, the design was up for an elimination based on the need for more research, the complexity of design, and interest from the team overall. If it was decided that it would not be eliminated, the need for research was identified. We either start all the way back from the beginning, or we modified that design to go all the way through. This process repeated until we refined design where there's no concerns and we had one that we chose. An example of this is shown here for our initial golf head design when we were using the club. There was 4 designs here, each featuring a slightly different mechanism for hitting the ball. This one used bevel gears to change the pitch of the face. This one was a thin rod. I know it's hard to see, but it was a thin rod that would basically, based on the position of where the rod was located, it would change the launch angle of the ball. This one used bevel gears to change the pitch of the face.
And this last one used a rotating shaft to change, had fixed faces that would change based on what need that we had. This last one ended up being refined into this design here where it was more fleshed out. You can see the rotating it here with a putt face and two different chipper faces, powered by a servo on the side, and the option to move this away based on how we wanted to balance the initial mechanism. However, after the rule clarification around week 6 of this semester, we decided that it was much more beneficial for us to go with a robot that could pick up, aim, and then launch versus trying to get the exact angle every right to hit the ball normally. So with that in mind, we came up with a rapid fire design process where each member created a fully fleshed out design of a robot. This one still being the original one that we came up with from the initial process, just to see how it would face up against the new designs. Each design was evaluated based on its complexity, its overall completeness, the reliability of its mechanism, and the repeatability of its mechanism. Going through, we gave the highest weight to the completeness because we were worried about timing. Our project, our final deadline is advanced a little bit more. We have to be ready by April. So going through all of these, Design 2 was chosen as the one that would be most probable to be successful. This design features a tank drive, an overhead flywheel mechanism with a passive passive intake on top, and a V4P mechanism that allows it to come down, putt, come up, and chip in a 360 cone around the robot.
So we began our feasibility study to make sure our design would work. So we want to start off with structural integrity. We're using a lot of off-the-shelf parts like T-slot, standard hardware. So we wanted to go for like minimal deflection, so that way our shots would be accurate. And we wanted to overbuild it for reliability because we were kind of running out of time at this point. So if we made any changes to the design, we didn't want them to like make our robot fail. So we did some basic FEA just to make sure that nothing was going to like bend way too much. Then we moved on to the studying the motors to make sure that all the motors we had picked out would work. So we found out that we needed specific movement speeds for each individual component of the robot so we can make our shots on time because we have a limited time. So we came up with a list of average speeds and accelerations that we thought we would need to meet with each component. And then from that, we were able to develop the torque and top speed needed for each motor. And then we compared that to the actual properties of the motors that we had already picked. And as you can see, all of them worked out well, except for the pitch speed, which was the top speed was significantly too low. So all these were done using constant acceleration. So then we switched to using a non-constant acceleration profile for the pitch motor, which allowed us to accelerate a lot faster. So we reach our top speed sooner, which was lower, but allowed us to still have the same area underneath the curve, which is how much we were turning. So we could do the same movement in the same amount of time with just a lower top speed. And then from there, we moved on to the preliminary design.
Yeah, with the feasibility completed, we started detailing and completing our CAD model. So this is the chassis that we went with. It consists of 6061 1/4-inch aluminum alloy plates with T-slot extrusion between them for ease of mounting the shooter mechanism to it and electronics. And we identified these side panels as potential critical members. So we ran an FEA analysis on it with all the mounting points incorporated. We got a maximum stress of just 8 megapascals, which is well below the yield stress or where any permanent deformation would occur for this alloy. So the drive base mounts to the sides of those plates, kind of a cantilevered tank tread design. It uses a 5M timing belt profile for the tank treads on the sides with ball bearing mounted pulleys. This belt path ends up being about 1060 millimeters with a 64.5-degree approach angle. This is so that we're able to just drive up and over the 2x4 and onto the platform. Because the belt sticks up higher than the platform is, we can just drive into it and the robot will just go up and over. And currently we are testing 3D printed belts for these sides as opposed to traditional belts, but pending the results of that, we may end up switching back to traditional belts. We have a little bit to adjust with the design on those. So this is the shooter assembly that mounts in the middle of that chassis. It features variable launch height, variable launch angle, adjustable launch direction, and adjustable launch speed, along with an integrated passive intake. so that we didn't have to design another second mechanism to pick up the ball and then hand it off to this, which would potentially be another potential point of failure. So to improve the reliability. So that shooter tube shown is mounted onto what's called a virtual 4-bar assembly, or V4B. This is what allows us to use the same tube for chipping, for putting on the ground, and for intaking the ball using the passive cone intake. It's driven by a GT2 belt for the pitch adjustment with an integrated encoder on a 26 RPM gear motor. And the V4B is controlled by a 52 RPM gear motor with an external encoder, again, for feedback control, so that once we are programming it, we're able to control it and make it do what we want to. We identified these links as possible critical members, and we ran an FEA analysis on them using the end forces and the torques acting on it. And we got a maximum of 0.05 millimeters of deflection while in use, which would be well below any deformation, as well, indicating that our mechanism should be quite stiff once it's assembled. So that shooter assembly is mounted to this turret, which allows for the directional control of the shots. It is supported on a large ball bearing and run off of another GT2 belt and another 26 RPM gear motor, and with integrated encoder for feedback control. And currently the turret is optimized for 3D printing so that we're able to quickly manufacture them and then test them to identify any changes that need to be made. But eventually we will look into simplifying the design so that we may be able to machine them, or potentially look into some high quality 3D prints. And this is the cross-sectional view of this part, the shooter cone. It, like I said, it's the intake and shooter integrated together into one mechanism. It has this cone on the outside that, when it's rotated this way and brought down on the ball, it centers it into the tube. The flywheel slowly rotates in reverse to bring the ball into the tube once the cone has centered it. And this servo has an arm attached to it that captures the ball and holds it until we're ready to shoot it. And then when we're prepared to shoot, the flywheel spins up with a maximum of 40 meters per second surface speed. And then the ball is released into the wheel by the servo. So that allows us to reach a target RPM to control the power of our shots, the speed. And on this cone, we did some calculations, and we found that in order to achieve that centering effect, we would need roughly a 15-degree cone angle, just summing torques on the ball, because the ball rolls against the ground, but it slips against this surface. So the friction that really matters is the friction between the ball and the plastic. So yeah, we found that 15 degrees should be reliable.
And moving away from some of the mechanical stuff, but for the electrical stuff, so our robot, the final design, we plan to use a Raspberry Pi, an Arduino board, various motors, motor drivers, and encoders. Currently, our robot runs off of just an Arduino Mega, 2 motors just for the driving capabilities, and the controller that you can just see on the left right there. And then for our software, initially we used some MATLAB just for initial testing and getting motors working, encoders working. And then, well, we do plan to just never use MATLAB again and just use the Arduino IDE to program the rest of the robots. For our budget, we got the initial $1,000 from the MSW grant. So we have spent $600 of it already. That's mostly on stuff like motors and materials, bearings, bolts, stuff like that. All for the robot. So most of our really expensive stuff is taken care of already. We don't plan to make any major changes, but we do have some purchases that'll most likely come underneath the $300, $400 limit that we still have remaining. And then for the project management aspect of it, this is just a little cut down of our Gantt chart. So we want to attain minimal motion, which is generally what our robot still is at right now. We want to get that on the 16th of November. We're gonna finish our first design on the 19th of January of next year. We're gonna finalize our design on the 1st of March. Then we gotta get some driver practice in before the competition date on the 7th of April. And we want to finish our final report and poster on the 26th of April.
So in order to do this, we need to have some next steps planned. So the mechanical team will be working on constructing the first prototype for the shooter mechanism. So currently we have the chassis assembled, but we still need to work on the shooter and turret. And once all of the designs have been fully finalized and optimized, we'll be making a lot of the parts from machined aluminum or higher quality 3D prints where needed. The electrical team will be working on all the code for the Raspberry Pi and the Arduino and getting that all worked out. Then they'll be working on the control system for the operator to use. And we'll also have to determine the size of the batteries that we need based off of the power draw of all the motors and components. And then the analysis team will be working on refining and optimizing the shooter mechanism to make that light and strong and reliable. And then the control system also needs to be worked on in order to make that as easy to use as possible and also accurate. Once this is all done, we will be delivering a fully functioning robot to compete in the ASME SDC competition this spring. And we'll also be working on the videos for the pre-competition scores. And we hope to be very successful in competition.
So in conclusion, the steps that we performed were performing background research, generating general specifications for the initial cutting design, and then we generated that initial design. This is where the rule clarification came in. So we went back to generating specifications, update it to that rule, generating the design again. Then we performed the feasibility study on our preliminary design, built that design. You can see it in the CAD and it's also here. And then as for team expectations going forward, we are on track right now to complete the robot in time to have plenty of driver practice and get those competition videos made. And we also plan to complete it under budget. As Elijah said, most of our major components have been purchased already, and we don't foresee any major purchases coming forth. Any questions?
So which operations are manual and which are automatic, which are open loop, which are closed loop in terms of the motions?
So we are planning on having manual tank driving control based off of velocity control with our encoders. The putting motion, we're gonna have programmed end stops so that we don't crash into the robot frame. And we're gonna have a programmed closed loop path for going from intaking to shooting so that we don't crash the robot again. Everything has encoders, so we're going to be running closed loop with pretty much every motion.
Is aiming for the shot manual from the operator?
No, we plan on trying to have each hole have their own preset operation so that the robot could just be set up and we'll know what it needs to do there. There will be an option for freehand to be able to manually shoot unless a ball goes astray and it's something we need to plan for, or if during the elimination round when the order of the holes is determined by not us, we can try and use the freehand to adjust whatever presets that we have.
So like the way you have the like the funnel for like to pick up the ball, like if the ball like happened to be positioned like against a wall, how would you be able to like pick it up?
So at the beginning of every hole, the ball will be reset to the tee.
Yeah.
So that's going to, we won't have the ball against the wall at all.
So like it's not like a multi-stroke hole ever. It's like you try and get a hole in one every time.
The goal is to get a hole in one every time, except for hole 2 here. We'll have to take a stroke there.
Okay.
And then that's where our tolerance comes in, the 6-inch. This 6-inch tolerance, we don't want to have a case where it gets against the wall.
Okay.
If it gets stuck against the wall, that's a 1-stroke penalty and a 30-second time penalty to reset the wall.
Sure. How did you like decide the like the 64.5 degree like pitch angle for your tank treads?
So that was more so a function of all the other designs. So with the design we have now, the idea was that we could incorporate, like, if the shooting mechanism didn't work and we wanted to switch to one of the other designs, we'd be able to add those attachments in. So there was a lot of constraints with like how long the top part had to be and how long the bottom part had to be.
Okay.
So that angle just kind of happened as a result of that. It wasn't really just picked
Sure.
to get over the wall.
And then we made sure that it won't tip over with that angle.
Okay.
Yes. Can you guys explain why you brought these things in here? What are they?
So, yeah, sure. So a lot of these are models of the obstacles. We have to submit one of the pre-competition videos is us completing all of the obstacles, and so we have to make models for that. So this is although this is one of the chip shots I have to do. That's one of the gates. There's going to be like a little motor that controls the gates. We have to find that more precisely. And then, do we want to demonstrate the
robot? Yeah,
robot?
this if we have time, we figured that if there
Yeah,
were.
just 1 minute, maybe. Yeah, to run it, a couple of more minutes.
Sure. I don't know.
Yeah. Oh, just like what? Oh, yeah. The way it is. No, you just need to focus on it. Here, there. You get all? Yeah, no, it's not my. Oh, yeah, it's. Or certain presentation. Oh, there we go. This is one function all the way. You drop
A little bit of movement. It works a little bit better on carpet. And since we kind of had to adapt last second to get some of the tank treads just printed with a TPU, it's a little bit too stretchy for our liking. It's just what we had on hand. And just the pulleys aren't necessarily designed for a 3D printed belt, but it does have some general movements.
Yeah, batteries are in spec, so variable power supply just zip ties.
All right, that's very good. Thank you. Usually when everything goes to take it to competition, it doesn't work right there. So just be careful for that one.
Yeah.
That is interesting. So.
Yeah.
Julia, gonna come here.
I'm coming.
Yeah. On stage. All right, Austin is here to go.
Alright, so our project was creating a feasibility study on an M-class rated dust extractor for a Milwaukee tool rotary hammer. So here's an introduction to our group. I am Tyler.
Grayson, how?
Eric Feasky.
And I'm Jacob Longstreet.
Alright, so our project purpose was to do a feasibility study on creating a Class M dust extractor for a rotary hammer. It is going to be based off the 2912 DE dust extractor, which is currently in production. So this would be a new to market feature for these dust extractors. As Class M is a European standard, usually for a big standalone on the floor type dust extractors with a hose. So this will be converting the one of these smaller integrated systems that goes on the rotary hammer to that standard. So in the workplace, concrete dust is a dangerous health hazard. Over a period of time, exposure will cause scarring within the lungs, and that will lead to silicosis, which decreases lung capacity and causes permanent damage. And here's an overview of the existing production tool, just to get you familiar with what is inside when we talk about things. So up here we have the whisker biscuit. So this is a circular brush that allows the drill bit to go through and creates a seal so that dust can't escape when we're extracting dust from the hole. Dust comes up through that way, goes down into this telescoping tube, which is spring loaded, so that as you drill further into the hole, we maintain contact with the workpiece and maintain a good seal so we're not leaking any dust. Goes around this elbow here and then into our dust collection box, which is green here. Travels around down to the bottom and then to our HEPA filter. And then through that HEPA filter, the air goes through to our fan, and then the exhaust is on the other side of the tool. And then this is powered by a DC motor, brush motor. And then this system in production is powered by the battery on the back of the tool. And it connects pretty similar to the way a battery does. It snaps together with a button. So the deliverables of this project is we are to do a summary on the where the current existing tool, how much of that meets the Class M requirements, and then what it takes to get it to the Class M requirements. And then the second part is to take one of these production models and make a fully functioning prototype that demonstrates what it takes to get the machine to Class M standards. So the constraints we had is the prototype must retain the features of the existing production model. So it has to be cordless, and then the performance has to meet or exceed the performance of the existing production model. We have a $5,000 budget, and we're limited by MSUE and Milwaukee Tools prototyping facilities. And we were not given any clear constraints on size, weight, complexity, or final cost of the product, as this is a feasibility study. So these are the Class M requirements that must be met to meet the standard. So we need a 99% filter efficiency, a 99% assembled machine efficiency. The auto cleaning feature must not negatively affect the performance of the machine. And then it also has to survive intaking upholstery tags. And these first four were tested already by Milwaukee Tool and passed by the existing production model. Now, the next couple here, we were able to inspect the tool and it was able to pass. So it has a disposable filter, and you can't accidentally remove this filter by swinging it around or just normal operation of the tool. It's a couple step process to pull it out. Yeah, and then the exhaust cannot disturb dust on the floor. So when this tool is in operation, the exhaust is on the side of the tool and it's off of the ground, so it's not going to do that. And then these parts of the standard, this is what we focused on for the semester here. So we had to do some testing. So we had to do a burst strength test on the filter. We have to do a suction performance test based off of our auto clearing function on the tool. And then we have to check the hose resistance to make sure that it's less than 1 mega ohm, so we're not building up static electricity as these dust particles are traveling through. And then the big thing in the standard is we need an indication when air velocity in our largest tube drops below 20 meters per second. So we need a way to measure that and then alert the user. And then the tool needs to be properly labeled with all warning and safety information.
So the first test we started out with was testing the HEPA filter itself, and it's called the burst strength test. And basically what you do is you clog the filter, and it basically can't have any visual defects after it's been clogged for 3 minutes after performing 3 minutes of like a burst strength is what they call it. So you basically clog the filter, cover the inlet for 5 seconds at a time, let go, cover it again, and you do that repeatedly for 3 minutes. And then you visually inspect the filter. So on the left here, that's the clean filter before any material was in it. On the right is after the test. It was clogged, but there was no defects to it at all. So it did comply and pass that test. That one's good. Next test we did was a suction performance test, and this is basically testing the auto pulse, which is that hammer and solenoid that he was talking about earlier in the diagram. And so for this test, you basically get the initial air velocity, and we used a hot wire anemometer to do that. After you get the initial velocity, you're drilling into the material for, we did it for 5 seconds at a time, just so you can get like increments basically. And so after each 5-second interval, you measure the new velocity. And we did that until the velocity basically dropped 50% for the airspeed. Once it dropped that 50%, we let go of the trigger, then the auto pulse occurs, and then you reapply the trigger and measure the new velocity. And to pass this test, it would have to be greater than a 20% increase. So here's the results from that test. You can see on the left-hand side, that's the clean filter with the clean air. So before we were drilling into any material. And then you can see it slowly decreases as the filter becomes more and more clogged. And then on the farthest right-hand side, that's after the auto pulse occurs. So when we calculated it, it came to a over 70% increase, which is well above the needed 20%. You should notice though that on the furthest left with the clean air and the clean filter, the tool itself does not go above the 20 meters per second, which is needed for this tool, because we have to be able to monitor when it drops below that. But it did pass that suction performance test. So after we kind of did those initial tests, then we could really focus on these next ones, specifically getting the tool to have airspeed higher than 20 meters per second.
Right, so that, like Jacob said, that first part was just getting a baseline on the tool. So really the design portion of this project is complying with this requirement with getting the velocity sensor in for the airflow velocity. We still need to test the hose resistance that kind of snuck up on us, so we'll talk about plans for next quarter. But this is the big design challenge, and we're not really gonna talk about like engineering design without warning labels because it didn't require engineering design. But yes, this is the main challenge here. And a big part of that was that currently in the tool, it doesn't get up to 20 meters per second. It needs to be above that, so it has room to drop below. Deciding what to do on this was a little weird because the standard is currently written for like current dust extractors on the market, which are, they're the standalone ones with like kind of like a wet dry shot back that attaches to your tool with a long hose. So that's what they're talking about with this hose velocity. It needs to keep the inside clean of dust. So when you turn it off, there's some dust coming out of the machine. So we just took a best judgment on how this applies to this integrated tool. We took the largest cross section of the tubing within the tool, and it turned out we got info from Medco, and it was at 13 meters per second right now. So we needed to increase that. So there's a couple ways you can do this. You can shrink the tubing in the tool, and from conservation of mass, this will speed up the airflow. We didn't have a lot of room to shrink the tubing before it would match the size of all the other tubing, and wouldn't really be desirable in general. Also, the part we would have to shrink there, that's part of like the vacuum port on the dust box, so that would interfere with being able to take the dust box out and vacuum out the dust. You could also try to reduce the pressure losses within the tool to increase your airspeed. Thought about adding vanes or somehow smoothing out bends in the tool to reduce pressure losses, but there wasn't a lot of room there, especially because the filter is the main restriction on the airflow. It takes over a majority of the pressure drop. So what we ended up doing was just increasing the fan speed and creating a greater pressure head from that, because it gave us a much bigger increase in airflow. So to figure out how fast we needed to spin the fan, we started off, we got the current performance of the tool from Milwaukee Tool. So we knew it's operating at about 24,500 RPM, and motor puts out about 35 Newton meters of torque at that speed. So we just shot for a 25 meters per second airflow rate. We're going to need to figure out how fast it really needs to be in testing. But figuring out how much faster we need to go is really just using similarity laws. because we already know the current performance. This does assume, no Reynolds number effects, which is a good assumption, because the rating numbers are really high in this scenario, around like 40,000. And then it's also assuming no relative roughness effects. We didn't change the fan at all. We're using the same fan. So that'll actually be exactly the same as far as that goes. And then you can see here that based on the dimensional analysis that drives these laws, the flow rate is proportional to the fan speed. And then power is proportional to the fan speed, or fan speed cubed, and the torque to its squared. So once we figured that out, it was just a matter of speccing out a motor. And we actually shot for a higher RPM just so we could be conservative. So really what we did is we went for brushless RC motors because they gave us a lot more, they gave us the performance characteristics versus the cheaper brushless or brushed motors. So it gave us these on the website, and we can plug it into a motor curve calculator and get all of our performances as a function of torque. This is a lot of curves, but all we're really worried about here is this black line, and the pink curve. That is the speed of the motor at a given torque and current. So we just had to make sure that at our 60,000 RPM that we were targeting, that we would have enough torque to overcome the aerodynamic load. And then we had to make sure that our current wouldn't go over the max current of the motor, so we wouldn't burn it out. So yeah, you can see here that as torque increases to fully loaded, it goes from your no load highest speed to your to stalled out, and then you have your minimum current at no speed or no load, and then the current goes up to its maximum at when it's fully stalled out. So yeah, those are motor selection.
And in order to house the new motor, we had to change the housing within the tool. On the far left, you can see that we had to create a new CAD model of the housing of the tool itself. We sent that 3D CAD model to Milwaukee Tool to on the print for us, as shown here in the center. And then here on the right, you can see it with the new motor installed, the entire housing system in close-up view. Which once we have that all assembled, we are on the left, we tested it with a battery and Arduino to make sure that it ran properly. Once we confirmed that it ran properly in that setup, we inserted it into the tool shown here. Right here, you can see we also had a current sensor to make sure we didn't burn out the motor. And up here, you can also see we have the anemometer we used for testing, just inserted into the side of the tool. For a comparison between the old Milwaukee Tool motor and the new motor we have, on the left here is the Milwaukee Tool motor graph. That graph averages about 15 meters a second squared for the air velocity, compared to our new motor, which gets up to at least 30 meters a second. We're not sure how fast it actually can go because our testing anemometer can only reach up to 30 meters a second. However, since having an anemometer into this side of the tool can cause variable pressure loss, we decided to have an integrated pressure sensor to measure the airspeed. In order to measure this, we went through a couple of different ideas. First, we started with the pitot tube. However, this pitot tube was undesirable because they work best with well-developed flow, and our tool never reaches well-developed flow. Then we went on to anemometers. The hot wire anemometer and the turbine anemometer both would be unlikely to survive the conditions within the tool, or we would need constant recalibration. Then we went to differential pressure meters, such as an orifice nozzle or venturi meter. These were undesirable, however, since they would need a pressure tap both on the clean side of the filter and the dirty side of the filter, which would leave them open for dusts, which could clog the meter. Instead, we went for a static pressure tap just in front of the fan. Not only was this the best option in terms of where it would be tapped into, which would be the clean side of the filter in front of the fan, but our Milwaukee Tool's competitors, also chose the same approach as shown in the pictures. In order to determine how sensitive our pressure sensor would need to be, we ran our similarity laws again, knowing that the current tool ran at about 2,500 pascals and how fast we're increasing the motor speed. We knew that our pressure had to be roughly 15,000 pascals. Over here on the left, you can see our new DOB differential pressure sensor, which had a range of up to 35,000 pascals. And here in the center, you can see exactly where we tapped into it, which is just after the clean side of the filter, but just before the fan. which this pressure sensor would talk to our motor control board, in this case a Metro Mini. And next turn, we will be hooking up a speaker to these Metro Mini in order to send us a audio warning when the airspeed drops below 20 meters a second. And in order to double check, make sure that this pressure sensor does in fact work, we ran a test. Let the tool run, get it up to airflow, let the pressure drop, then let the pressure recover, and then turn the tool off. And the graph, as you can see of the pressure sensor, it was able to catch the rise, the pressure drop, the pressure recovery, and the tool turning off.
Yeah, so in summary, this semester, we were mainly focusing on understanding this, the dust class M standard, and where the tool currently complies. And then we did get a prototype going showing that it's feasible, that we weren't even sure if we could get the airspeed above that 20 meters per second. So we showed that that is definitely feasible. And then going forward, we're still gonna have to test the hose resistance, and potentially make a design for getting that below 1 mega ohm. And then kind of following off of that. So our next steps will be first of all, getting this fully functioning prototype working. There's some stuff we have to do as far as getting the like the old electrical components integrated into our prototype, and getting the auto cleaning hammer to work. But we also need to like give Milwaukee Tool a good idea of how this like modifying this to be class M compliant is going to affect the end user. So a big thing is if this thing starts throwing off airspeed warnings, the airspeed gets super low immediately after you start using it and the dust box is not even full. That wouldn't really be great for the end user. And then also, I mean, this is a really powerful motor, and as you saw, the power required is like proportional to the fan speed Q. So it could be like totally the case where this thing takes a ton of power, and with battery powered tools, that's really important. So that may rule that out if we have to run the fan that fast. And also with that, it draws a lot more current than the current one. And since we're running off of one battery, not sure how much the current the drill draws, and we haven't looked too much into that. But if this fan is taking up too much current, these lithium-ion batteries have a certain amount of current that they can discharge, like within safe limits. So that could knock this idea out if we needed too much current, basically. We also need to figure out if it passes European noise regulations as far as not so much about the decibel levels, but it's more about the frequencies in this situation. So we need to do more analysis on that, and how much this motor does generate more heat. So we have to figure out like what the thermal situation with that is. And I already talked about how the electronics will be integrated. But yeah, so there should be more analysis to do as far as like the fan goes, and finding the exact power requirement with that too. We did some like preliminary CFD stuff, and we're not running the fan at its designed operating point. So it's not really in the scope to be modifying this fan since impeller design is pretty complicated, but it could be dropping our efficiency by around 20%. So it would be a good idea to see if we can change blade angles or other geometry factors and increase that efficiency, or see if that's something we just have to deal with. So yeah, that concludes our presentation. Questions?
So you did mention noise at the end. I had questions about that. So first of all, European versus US, is this targeted just for Europe, or?
Yeah, it'll just be Europe. So yeah, they don't really have OSHA over there. They have their own regulations. And just from looking into it, it was just decibel stuff, but we do have to do more research into that. We also have to add vibration dampers to the tool. That's what the old tool had on that motor. It had little rubber bumpers that hold onto the motor. Ours is just in the 3D printed casing. So we do need to add those, and that will probably help.
Did you experience a lot more noise when you tested it?
Yeah. And so we did add a little bit of rubber in there right now, and it made it a lot better. But yeah, it was noisy, and it is louder, absolutely, because it's running so much faster, and it's even getting a little bit compressible at those speeds. So it's pretty loud. We can do a demonstration maybe after.
No.
Yeah, I have a couple questions.
Yeah.
So when you're measuring your pressure, measuring through that tube.
Yeah, so there's the sensor in there and then it hooks up to the, right in front of there's a little port in there that the silicon tube goes into and it's measuring the static pressure in front of the fan. So as you're at a constant fan speed, when there's resistance, like it gets clogged, there will be less air load on the fan, and so the fan RPM will be able to increase, and that'll increase the pressure rise. And then also depending on the performance curve of the specific fan, at those lower flow rates, if you look at the performance curve, it's a decline. So at the lower flow rates, you're going to have a higher head rise. So the head rise should increase with more resistance.
And then when you're measuring this, are you measuring the air that's by the fan, or is the pressure being taken through that smaller tube? Measuring through the tube, then now you're not measuring through your biggest or deep.
Yeah, no, it would be purely, it's going to be like purely correlation. So yeah, it's not measuring directly through like where we are interested in the airspeed being. We would be measuring with the anemometer or like maybe like a more refined like Venturi meter or something on the outlet. But we would be measuring that and then just correlating that with the pressures we're getting, because that should just be a function of, like the speed in there should be a function of the head rise of.
Yeah, we're basically measuring them both at the same time, plotting both of them, like overlaying them basically, and then just getting a correlation between the two. And then we'll basically program that to be like when it drops or when it gets to this pressure, send a notification that the airspeed is below that speed.
Yeah, and that seems to be what the current class on vacuums do. They hook it up right by the motor.
Then other question that you kind of touched on, so like you're ramping your speed of the fan now higher. Is that within your scope to look at how your current draw is? Because like you're upping your current draw, that could cause like bad user experiences, whether it's like runtime, over temping PCBAs. I don't know if that's within your scope, but it's something to have in the back.
No, yeah, definitely. We're definitely hoping to get like an accurate number on exactly how much on how much more current we need. Like it's kind of arbitrary what speed we're going to be shooting for. We're going to have to do testing and figure out do we need a 25 meters per second, or 30 meters per second. So that will change that. But we're hoping to give Milwaukee 2 a really good idea of how much more current this can be. Because yeah, that would kind of be a killer if it like took the operating life and put it way down. So yeah, thank you.
Yeah. This might not be like the most relevant thing for your part, but could you explain what you mean by the like 99.9% machine efficiency as kind of?
Right, yeah, so filter efficiency is how good it is at blocking or at filtering particulates. So that would be like it blocks 99.9% of, there's a specific like 0.3 microns or something that it needs to meet, but yeah, that's what a filter efficiency means. And then also the HEPA filter can be really good, but your assembled machine has to have good sealing too, so it doesn't like get dust out everywhere. So that's why you have to test both of those.
What wattage the current machine as sold runs at?
I know the power draw of the dust extractor fan. It's like 85 watts nominal. And this thing is like the motor we have in there at full throttle is way higher, like 1300 watts. It's ridiculous.
Because I've seen breakers using space heaters that are like similar wattages.
Yeah, that was the thing. We had to run it off a battery. We were gonna like maybe try to test it with a power supply, but like right now, if we ran it, we actually bought a bigger battery and it would like a 20-volt battery and it would draw like 60 or so like 70 amps. And we got that like over 30 meters per second, just with a smaller like 15-volt battery. That was like drawing like 30 amps, so it was pretty crazy. But so we can probably downsize the motor still, and use less power, at least throttle it.
Is weight considered, because this is a handheld machine? You guys add a lot of weight to the tool?
It would be more weight with Probably just, this motor is actually lighter and smaller. It is more expensive than those like can motors. But right, if we did brushless, we would need a controller, so that might add a little bit more weight. You need like the MOSFETs and stuff, and it's a little bulky. But that's definitely something, like that's the purpose of this, is to find out exactly how much weight it's gonna add. So we want to get as low as possible, but yeah, currently we shouldn't be adding too much.
Part of our deliverables was a qualitative analysis of did we increase the weight and the cost and how do we do so?
You mentioned that one of the requirements for an M-class structure is a warning when the velocity goes under 2 meters per second. Right now, your aim is to add a little speaker, right?
Yeah, we actually have one in there right now, and it's pretty quiet, so we might bump that up. You can either do an LED or a speaker, so we might do an LED.
I was gonna ask because usually when we're running the tool and when you're drilling into something, the drill is gonna be loud enough. That
Yeah.
If your speed drops, I don't know if you're gonna be able to hear whatever speaker you put in there.
Yeah, that's what I was thinking too. I mean, we could put a big speaker in there, but it would kind of be silly. So yeah, we were thinking it would probably be best to do an LED, because also if this warning is going on super early and like the dust box isn't full, like we were talking about, then if an LED, like a warning LED just came on, user wouldn't really care about that, and they could just use the tool normally. Versus if a speaker was coming on and like the warnings were coming on, it would be super annoying. So yeah, we have the choice of doing either, so we'll probably do LEDs.
Any other questions? All right, thank you. This is our section. We will take a 15 minutes of break and attend other sessions if you like. Otherwise, you're done with this one. All right.